So let's find the pH of the solution. So again, our first step is to let the acid and base react. And I think it would help you if you would write out what step 1 is for right now until you can kind of get the gist of this, and you can speed it up by eliminating that. So here we have I'm going to do the net ionic. I know that's not going to dissociate, but the sodium hydroxide, sodium's going to be a spectator. And so there's my strong base. This is not an equilibrium. It's a neutralization reaction. And the acid will donate the proton to the hydroxide, and it will leave you with the conjugate base and water. And like I said, because water's a liquid, we don't worry about it. Okay. So I'm just going to kind of mark that out. And remember, we're going to do our ICF, initial, change, final. So initially, what do we have? Well, I gave you 25 mils of 1 molar acid. So we're always going to start these with 25 millimoles of the acid. Okay, so I'm not going to do that calculation each time. M times V gives me that. So we're going to have 25. I'm adding 10 mils of 1, so that's going to be 10 millimoles, and I'm not going to worry about sig figs right now. So I get 10, should be 25 and 10. And then we don't have any of that initially, right? We haven't made any of that. And so now I'm going to say this is limiting. Add 10. So at the end of the reaction of the neutralization, I don't have any excess base. I have 15 millimoles of that, and I have 10 millimoles of that. And that's what I have at the final. So that's step 1. I let them react. Classify the beaker. So what do I have in my Erlenmeyer? I have HA and A minus. And that, because those are a conjugate acid-base pair, is a buffer. So that just put that so I remember, oh, don't forget, it's a common ion. This won't be 0 in my next equilibrium table. And so then I go to equilibrium. And because it's a weak acid, I do the weak acid equilibrium. There we go. Weak acid equilibrium. So this is my rice table because now I'm in equilibrium. Remember. All right, so initially, I've got to get these concentrations. So that was step 2. I got ahead of myself. Step 2, I'm going to find the concentration of HA at this point. That's going to become my initial for my equilibrium table. So I'm going to say that is 15 millimoles. My total volume is 25 plus 10, so 35. And that's going to give me a molarity. And then I'm going to do the same for that. 10 over 35. And that's going to give me a molarity. So here we go. If we take 15 and divide it by 35, we get 0.43 to 2 sig figs. 0.43 molar. And then if I do 10 divided by 35, I get 0.29. 0.29 molar. Now, if you want it to come out as decimals, I always have to put the 0.0 or it doesn't do it. But so there's my concentrations for step 2. So this would be step 3. Set up your rice table. So these become my initial concentrations that I have in this beaker. So HA is 0.43, and this is 0, and this is 0.29. Common ion, don't forget, this is where the common ion comes in. So this is the weak acid dissociating, but it has the salt already there from the neutralization reaction. So that's why I have to start with some of that in there. All right, change minus x plus x plus x. And then in your table, you're going to show me that minus x. Please don't forget that. Even though we are going to ignore it because it's a common ion. So then we have Ka equals for acetic acid. You can look it up in the table. It'll always be given to you on assessments. And that is going to equal x times 0.29 over 0.43. You show it to me in the table, but you don't have to show it to me there. All right, so solving for x, and we realize x is the hydrogen ion. So it's the concentration of the hydrogen ion. And when I do that, I'm going to get 1.8 e negative 5 times 0.43 divided by 0.29, and I get a very small number, 2.7 times 10 to the negative 1, 2, 3, 4, 5. So that is my hydrogen ion concentration. pH then is the negative log of that. So negative log, I have to always add the base in, 2.7 e negative 5. And actually, just so I make sure I don't do a mistake by counting my decimals there, I'm going to do the answer. 4.57 for 2 sig figs. 4.57. So if I add that to our table that we've already done, we see we're not changing much at this point. It started to increase a good bit, and now it has slowed down. And why is that? That's what that word buffer means. Resist changes in pH. Buffer solutions resist changes in pH. So I added 5 mils and it went up almost 2 pH units, right? From 2 to 4. And now I added 5 and it didn't even go up a pH unit. Okay. So it's showing you, this is showing you it is resisting changes in pH. Well, that's because you've set up this common ion buffer situation.